So to continue our discussion of cation exchange on soil colloids, we talked about the various cations having a certain binding affinity series, which you can see along here, according to the valence, for the most part, except for hydrogen ions here. And so the higher valence cation, the more strongly bound the cation is to the soil colloid, whereas the lower valence cations are better at, have a higher exchangeability, so that they can easily be displaced from the colloid given any of these other ions in solution. All right, so let's take a look at now in the diagram on the right how the plant influences the availability of these cations. So how does the root influence the availability of cations that are bound to soil colloids? Okay, so what you can see in the diagram, that in one way plants are respiring carbon dioxide, and when carbon dioxide mixes with water, it produces carbonic acid. Let's see, H2CO3. And in solution, the acid here will dissociate into hydrogen ions plus bicarbonate ions. And those hydrogen ions right there, if we look back at our binding affinity series, can easily displace some of these lower binding or higher exchangeable ions. So that's one way that the plant can actually influence the different kinds of cations that would be coming off of the soil colloids and into the solution. Another way that we'll talk a little bit more about is called hydrogen ion extrusion, which is using a hydrogen ion or proton pump. Requires ATP to basically pump hydrogen ions out into the soil solution. And so as a result, they will again displace these lower binding affinity ions that are more highly exchangeable, making them readily available for uptake. So these are two ways that plants can influence the availability of soil nutrients in the soil solution itself. Okay, so after this exchange of cations and the cations enter the soil solution, then we could say ultimately here that the soil solution then is the direct source of nutrients for uptake. Okay, so that's where the plant is getting, its nutrients directly from. All right, so these nutrients are going to be taken up, and so then the next question would be, how are the nutrients in the soil solution continually replenished? How are nutrients, or let's say cations in this case, in the soil solution, which is abbreviated there, replenished after all this root uptake and perhaps some of the runoff of these ions? And the answer would be basically by cation exchange. That's the term we want. This whole exchange of cations up and down this binding affinity series that we've been talking about. So that's how the soil solution nutrients are replenished. All right, so how then are nutrients on the soil colloids replenished? Once they're exchanged, they've got to have a continuous, another source of input. So how are the cations that are to be bound to soil colloids then replenished. And there's a couple of different methods that we're going to see here below in this table, but not in the table is one of the first answer, which is basically, if we look back at this question, how do we get some of these how do we get some of these nutrients that have a lower binding affinity to be bound to these soil colloids? Because if they're covered with higher binding affinity ions like calcium or magnesium, how do we get any of this potassium or ammonium on the bound to the soil colloids? Well, one way here is that remember, the binding affinity series is only relevant or accurate if we assume that all the concentrations of these ions are equal up and down the series between the soil colloids and the soil solution. So otherwise, it takes a high concentration, high concentrations of these low binding affinity ions that are in solution to displace colloid bound high binding affinity cations. So for example, we're just going to write in the top here, we would need a high concentration of, say, ammonium ions in solution, in the soil solution, to displace bound calcium ions from the colloids. So that's how we get the colloids to store or to bind some of these lower binding affinity ions. So just stressing once again, that series is only relevant when the concentrations are equal along the binding affinity gradient there. Then if we add more of these lower valence cations, higher concentrations of these lower binding cations to the soil solution, then they can displace these higher binding ions. Okay. Now, two other methods of increasing or replenishing the nutrients that are bound to soil colloids. We see these two methods here, weathering and recycling. So this would be, say, number 2 and number 3. And if we've already talked about this in class, these numbers may not correspond with how we talked about them, but you can sort of match up in your notes how these should go. So the second thing in the list here is weathering, which is, of course, weathering of bedrock. And so you can see some of the things that are important through weathering, which includes calcium here. But if we're looking at the relative numbers, the percent total source of a plant nutrient, most of those nutrients are coming from what they're calling recycling here. And recycling is actually decomposition and mineralization. For example, we might see organic matter become mineralized, or let's say organic nitrogen becomes mineralized, producing inorganic sources of nitrogen such as nitrate and ammonium through the process of mineralization. So certain bacteria and fungi that would carry out that process. So by far, most of these nutrients are replenished on the soil colloids as a result of decomposition and mineralization. So this brings us back to a discussion question that we could ask in class, or did ask in class, which was basically, what is the effect of acid precipitation on soil fertility. How much, in other words, how nutrient rich the soils are. So acid precipitation deposits sulfuric acid and also nitric acid. And so as acids, these are going to be sources of hydrogen ions. So it's a good discussion to sort of see what is going to be the effect of adding these acids to the soil. So that's a topic for class discussion. And then the other question would be, how do we mitigate for this, the effects of acid precipitation to return the soil fertility to its natural state, or close to its natural state. Now, one of the things that we can see from looking at this kind of question and remembering our binding affinity series is that when, if we look at that series there, we have hydrogen way out here, which has that high binding affinity, and all these other ions, when they're in place, bound to the soil colloids, there really isn't a high concentration usually in natural systems of hydrogen ions. So there tends to be a higher concentration of these other types of ions, which is what we would refer to as, in contrast to what we see when we do have high hydrogen ions, what we refer to as base saturation. So when we have high concentrations of things like high concentrations of ammonium and calcium and magnesium, potassium, and so forth, then we say that there's a high base saturation in the soils, as opposed to being acidic. And so soils are most fertile when they are at this basic level where they have basic pH because of the low amount of hydrogen ions. So we try to see soils, soil fertility is maximized when base saturation is high. And then that leaves us with discussion of, we'll add it in here, what's happening with anions. All right, so we've talked a lot about cations, but the anions are things like nitrate and chloride ions, phosphate ions, sulfate ions, and these are certainly, important nutrients in the soil as well. But because they have those negative charges, they're anions, and they do not bind to the colloids. That means that they are always in the soil solution. I'll write it down here. In the soil solution. Now, some of these different cations and anions that we're talking about are more soluble than others. And so, for example, phosphate, which is this here, tends to be relatively insoluble. So even though it can't bind to soil colloids, it's also not, being washed away by the soil solution because it's not very soluble. Whereas things like nitrate over here is highly soluble and does move through the soil very easily in the soil solution. So we'll talk more about the soil solution and the gradient of ions in the soil solution based on their solubilities or their mobilities is what we refer to those as in the soil.